Hey, welcome to The Explainer. Today, we're pulling back the curtain on something you've probably never thought much about: the unseen symphony of a building.
Have you ever walked into a huge skyscraper and just looked up? Or stepped into an office and felt that perfect temperature? We take it for granted, but there is an incredible world of hidden complexity working behind the walls.
And that's because a modern building isn't just steel and glass. It's a complex interplay of systems, this amazing symphony of engineering. And at the center of it all, the architect. They're the conductor, making sure every single part, from the massive frame to the tiniest wire, plays in perfect harmony.
So let's break down this orchestra piece by piece, starting with the very foundation of the whole performance, the structural system, the part that literally defies gravity.
All right, so think about it. The first, most fundamental problem any building has to solve is a fight against physics. How does it handle the constant crushing pull of gravity while also standing firm against powerful sideways forces like wind or even earthquakes?
Well, the solution comes down to what engineers call the 4 S's of structure. First up is strength. This one's pretty obvious, right? The materials have to be strong enough to not literally break under all that pressure. But then you've got stiffness. Because see, a building can be strong, but it could still sway in the wind like a really tall tree. Stiffness is what stops that unnerving wobble. It keeps everything feeling solid under your feet. Third is stability. This is the big picture stuff, making sure the entire building won't just tip over or suddenly buckle. It's really the difference between a modern marble and a house of cards. And finally, the fourth S, synergy. Now this is where the engineering becomes pure art. The structure can't just work. It has to merge seamlessly with the architect's vision, actually making the design more beautiful and functional. So how do you fight those sideways forces? Architects have 3 main tools in their belt. First, shear walls. These are basically super stiff, solid concrete walls, often built around elevator shafts. They're rock solid, but they can limit your floor plan. Then you have braced frames, those classic X shapes you see on steel buildings. They're incredibly efficient, but they can get in the way of windows. And finally, there are rigid frames. Here, the magic is in the ultra-strong connections where beams meet columns. This gives you wide open spaces, but they're definitely more complex to build. Of course, the huge decision is what you build with. And that often boils down to a classic showdown: steel versus concrete. Steel is fantastic. It's lighter, it's stronger, and it lets you build way faster with these huge open spaces. The catch? It performs terribly in a fire unless you protect it. Concrete, on the other hand, is cheap and naturally fire-resistant. But man, it is heavy. That means you need bigger foundations, and it can have some problems in really cold weather. Okay, so the structure is up. It's solid, it's not going anywhere. But a stable building is pretty useless if you can't live in it, right? That brings us to the next section of our symphony, the mechanical system, the part that controls the entire inner climate. This system is all about one thing: our comfort. It answers the question, how do we turn this giant inert box into a place people actually want to be? How do we get heat, cool air, and clean water whenever we need it? To get a handle on a building's temperature, you have to know the 3 basic ways heat moves around. First is conduction. That's heat through direct touch, like a hot coffee mug. Then there's convection, which is heat carried by moving air or water. Think of how an old radiator warms up a whole room. And finally, there's radiation, which is heat traveling in waves, like the warmth you feel from the sun. So 2 of the most common ways we use these principles are with forced air and hydronic systems. Forced air uses a furnace to just blow hot air through ducts, which is great because you can use the same ducts for air conditioning. Hydronic systems, on the other hand, circulate hot water through pipes to radiators, which gives you amazing control over each individual room's temperature. And listen, mechanical systems aren't just about being cozy. They're about survival. I'm talking about fire suppression systems, things like sprinklers and the standpipes for firefighters. They are the building's automated first responders, designed to react in seconds to save lives. All right, we're stable, we're comfortable, we're safe. But what about power? It's time to tune in to the electrical system, which is basically the building's central nervous system. So where does the spark come from? How does a massive building take that super high voltage electricity from the grid and deliver it safely to every single light, every outlet, every laptop?
Well, that power goes on a very carefully controlled journey. First, it hits a transformer, which steps the dangerously high voltage from the street down to a usable level. Then that power flows to the switchgear. Think of it as the building's main electrical control panel. From there, it's sent out through circuit breakers, those safety switches that trip to prevent overloads. And absolutely everything is tied to a grounding system, a vital safety net that protects us all from electric shock.
Okay, so we've seen the different sections of this orchestra. The structural, the mechanical, the electrical. But the real masterpiece is getting them all to play together. And that brings us right back to the architect's role as the conductor, wielding that baton of coordination. In this coordination, it's not something that happens in one meeting. It's a process that is woven through the entire life of the project, from the big picture questions in pre-design to making sure everything fits together on paper in schematic design, all the way to solving the inevitable clashes that pop up on the actual construction site.
I mean, here's the core challenge in a nutshell. I want you to picture this, a giant round air duct trying to occupy the exact same space as a massive rectangular steel beam. It's just not going to work. As our source material puts it, all these conflicting elements, the ducts, the lights, the pipes, the beams, they must be resolved.
And to really get the scale of this puzzle, get this. Just the HVAC system, the heating, ventilation, and air conditioning, can take up between 10 and 15% of a building's entire usable area. Think about that. That is a massive chunk of space that has to be threaded perfectly through the bones of the structure without hitting anything else. What this all proves is that a building isn't just a silent container. It's a living, breathing thing, full of these complex systems, all working together in concert. So the next time you walk into any building, an office, a library, an airport, I want you to just stop for a second and listen. Beyond the hum of the lights in the air, what unseen symphony will you